almost 100% of what I focused on first semester was collisions, so that you would be effectively able to do collision parts of tests. What was left out, and it was sacrificed because of time, was any kind of discussion of impulse, and then something else. What does it mean to be a system? That has to include something that was on the exam, but I knew I couldn't cover in time. The center of mass. We need to clean up these topics, get them finished. So today, I don't have a whole lot of cleanup. I do want to remind you that we have stuff about momentum that I think was obvious. And so I want to do just the quick reminder. Momentum, a measure of inertia while moving. We know in a collision that the momentum of the system stays the same. I should remind you that there are examples of this that we talked about in class. The most appropriate example I can think of is just one object coming in contact with another. I described the fact that in a collision, the collision itself is just the instant before contact through to the instant after contact. I wanted to describe the fact that, like, in a situation like this, the reason why we study momentum and the reason it's an important quantity is because it can convey direction in a way that energy can't. But also there's 3 different ways in which these things can interact during a collision. There's the situation in which the kinetic energy isn't conserved, and we'd call that an inelastic collision. Remember, the momentum before will equal the momentum after, but the kinetic energy before will be greater than the kinetic energy after. It will lose kinetic energy. That is an inelastic collision. And a little more vocabulary, there's a subcategory of inelastic collisions. Do you remember what they're called? Perfectly inelastic. That's a vocabulary word, so if they say perfectly inelastic, they are telling you that the 2 objects grapple or connect so that they will have the same velocity after the collision. Okay? They are still an inelastic collision. These 2 rules apply. What's the name of the other kind of collision? That's right. If it's not inelastic, it's got to be elastic. And a elastic collision, of course, still conserves momentum, but also in this circumstance, the kinetic energy is conserved. Now, is it possible for the kinetic energy after a collision to be greater than the kinetic energy before the collision? Did you guys hear the question? Can you have more kinetic energy after the collision than before the collision? And the truth is, not without some other interaction, not without something else adding energy to the system. So you can have this circumstance, but having a greater than in this direction means there was something else there that added energy that was somewhere else and got added to the system. Generally, some amount of potential energy that might have been stored somewhere gets added to the system. So a kid jumping off a swing or jumping off a moving platform, they're adding energy because they themselves stored it and they jumped, they applied some kind of external force to do so. Just to ensure that we have all of us working together on this and you remember this stuff, can you treat this like a perfectly inelastic collision and determine the outcome real quick? I'm asking that to see if you remember all the steps to deal with a collision. So I'm going to ask you to give that a try. Remember, I tried to say it, and I tried to put hints here. Momentum is a vector quantity. So determine what direction is positive. Use that from the beginning. So we get, 8 times positive 4 here, plus 12 times negative 3. Right? Let's take the direction into account. So after we're done, they're joined together because they grappled. There was a perfectly inelastic collision. So 8 plus 12 times our unknown velocity. I mean, I know it's just a negative sign, but you understand it's a negative sign, right? Everything else is wrong there afterwards. So it's also important because in this case, the answer is negative, meaning that when this is done, the direction of the motion of the object is to the left, not to the right, which is something else I don't know how to put this in your notes. The most common question related to stuff like this is, what is the magnitude and direction of your answer? Now listen, you AP1 like transplants who used to be in C. This is kind of a thing that I need to make sure I emphasize. In AP Physics 1, the reason why people get questions wrong is they say, well, I indicated the direction. I left the negative sign there. That tells them it's to the left. It doesn't. It doesn't tell them it's to the left. They are asking you to explain why the answer is negative, which means you have to say the speed is 0.2 meters per second and it's traveling to the left. You can't, they want you to interpret the meaning of the negative sign. Whenever your answer comes out in such a way as to have a negative sign, or they specifically say magnitude and direction, you need to give the direction in a way in which it's clearly understandable. Now, in our class, they're okay with sophisticated ways of doing that. So left and right, maybe not, but if they have a drawing and they'll do this. They'll have something like that that's right there, next to the diagram that they've given you. This is code, and you have to understand this code. If they put one of these on the test, they are telling you what they call the positive X and positive Y direction. And you are expected to know this. So you could say, instead of left, you could say it's in the negative X direction. But you'd have to say negative X direction based on their coordinate system applied to the problem. From now on tests, look for this to be embedded. When I cut and paste pictures out of the actual tests, if that's there, I make sure I grab it. Because you need to be aware that if they apply that, they are telling you what they want you to use as the positive direction. Does everybody understand? I know I'm adding a little bit on top, but if they include one of these, they're giving you direction. And worse, they're not saying it, but eventually they're going to mean that Z is out of the paper or out of the screen. So they'll include all 3 dimensions. We will have some things coming up where 3-dimensional problems are going to come into play, and you're going to have to be sufficiently prepared for it. So if you see a coordinate system on the diagram, they're telling you the direction. And you can use that as your answer, but it's always best to be very clear about direction. Do not just leave it here. Does everybody understand? All right. So I want to focus a little bit on 2 things today. The first thing is impulse. I discussed it I blew past it. I want to spend more time on it. Impulse is defined as change in momentum. It's defined this way. And technically, there's 2 parts to impulse. Now, what I'm supposed to do here, I'm supposed to tell you that the symbol for impulse is a capital J, and I'm supposed to use that for this. But impulse is not used on the exam in the same way as other things are. So do you remember how I used to write out the word work for the quantity of work? I will do the same here, because the capital J just doesn't feel like it means anything, and I just can't do it. So I'll write out the word impulse when we're asked to use it. Generally, you're never asked to find impulse. You're asked to understand what the idea of impulse means. But that's about it. Impulse has 2 sides. And this side is the effect of an impulse. What happens? You can determine an impulse by looking at the effect. The best part about the effect side is that it doesn't matter what happened in the middle. It is just the final minus the initial. It doesn't matter how the transition occurred. Impulse just wants whatever the final momentum is minus whatever the initial momentum was. But impulse is a vector quantity. It has direction. Be careful. Impulse, the direction of impulse isn't in the momentum. It's in the change in momentum. Let me give you an example. Let's say that this is our object and it's traveling with some velocity to the right. And then something happens and the object is still moving to the right, but not as fast. What direction is the impulse? Now, this part, I'm not trying to be hard on you. I'm trying to just think about it for a minute. Something caused this change, right? So impulses are not momentum. Impulse is change. What was the direction of the change in the impulse? That has to be to the left. Now, it's easy to understand when you understand that impulse is force times time. This is the cause. Forces cause changes in momentum. That's not a surprise. Just like forces cause changes in energy. So, unlike energy, there's not lots of different kinds of momentum. There's one. So forces cause change in momentum. The direction of an impulse is the direction of that force. So if you're asked what the direction of the impulse is, it would be the direction of the force required to change the impulse. That's a big sentence. I'm not going to write it. If you are asked the direction of the impulse, it is the direction of the force required to change the momentum. If you're asked the direction of the impulse, it is the direction of the force required to change the momentum. Do I have to say that anymore? Did we do okay? I know it's a lot of words. I promise to be less wordy in a minute. Now, for the most part, we don't talk about this very much, but there are a couple of circumstances where you're going to have to do some things with this that are unpleasant. So I do want to talk about those for just a minute, but are we okay so far with this? The first thing I want you to know is that this is mechanics. So although true, this is the algebra version of this. What if your force isn't constant over your time interval? That's going to cause a problem. So there is another way to deal with impulse. It's unpleasant because it might bring stuff up that's hard, but the impulse can be calculated as an integral if your force is not constant over the interval. This is highly unlikely. But I want you to understand that the way this generally gets brought up on the exam isn't by giving you a function and asking you to integrate it. This is generally brought up on the exam in a situation where you're told that you have acquired force versus time data. And we're actually going to do this lab with my new carts. That the green cart collided with the yellow cart, and the data is on the graph. And the force on the green cart looks like that. what was the change in momentum of the green cart? Now, just so you know, what's being shown here is this. The green cart, not moving. Not moving. We now figured out what the AP chemistry slopes are good for. You guys didn't want them. It causes balance to the track. What's that? School is hard. It's hard to see you here.
I'll get this. It's this side. He's making another amazing one.
Yes, I heard. I'm looking forward to seeing who injures themselves this year. Real quickly, how much force is the green cart experiencing right now? We all agree 0? And then, how much is it experiencing now? 0 again, right? Nothing's touching it. So, there's only a small time in which the green cart experienced the force. Would you agree? That's what that is. And you'll see how it's linear like that. That's because spring forces are proportional to displacement. So you get 2 linear functions, one as the spring is being pushed in, and one as it's coming back out. Now, we could do integration here, but the most likely thing you'd be asked to do is to find this area, because that area would be the impulse. That's the most likely thing. Even if it shows up, it very seldom shows up. We're going to do a lab on it so we can do some practice, but it doesn't show up very often. Remember, this will equal the change in momentum of the car. Now, because I want to be thorough, the yellow car, it was not I guess it's not yellow, it's blue, and that's uh-oh. Am I colorblind? I was calling this the green car. What color? Is this green? I'm not crazy.
Could be.
Well, not why. The labels. I have labels. I know you can't verify it too far away, but this one says green cart, and this one says yellow cart. Now, there's no chance that's yellow, right? But I was calling this one the green cart, but that's clearly got to be the yellow cart. And this got to be the green cart. I know. Okay. So it's not me, right? Well, the problem is that I've already started it like this. So I'm gonna say at the other cart, I'm putting blue. I don't care. That's blue turquoise. It's turquoise. Yeah. I don't have turquoise as a color here, so if we do the lab the way I want to do it with my fancy new cars and stuff, we should be able to generate these graphs just like this. So the area under the blue graph would also be impulse, right? And this was a collision. So you'll notice that we would expect in a collision to have equal and opposite impulse. I'm going to say this again because I just want you to get this in your notes. I want something for you to study. You'd have equal and opposite impulse in a collision. Both cars changed their momentum, but the momentum of the system stayed the same. So the positive impulse that we have here and the negative impulse that we have here have to be equal and opposite. That way the momentum of the system stays the same. This generally is the most you really need to understand about impulse. You may be given a graph, bless you, where you have to go and find the impulse by finding the area under the curve. We'll do this with the lab next week. It's not a great lab, but we'll see if my new carts help. That okay so far? I don't really want to spend much more time on this. It's really not a valuable experience. So that's about the most we have to know about impulse. I know I talked about it a little bit first semester, but this is it. What I really want to spend our time on, if I can, because this is actually not as easy, is center of mass. And that also requires that we talk about a system. In your head, you're probably asking me, well, why would I say something like that? What does that mean? Of course it does. Well, in reality, gravity acts on the whole object all the time. If I break the object into pieces, gravity acts on every piece of it. So why am I saying gravity acts at the center of mass? Well, we are sometimes faced with problems that require us to try and figure out how an object will behave. So imagine a box. And I'm going to tip over the box. Well, how far do I have to lift up the box before gravity will tip it over the rest of the way? Do you guys understand what I'm saying? Some things are top heavy and will be pushed over easily, while some things have a low center of gravity. Have you heard that phrase before? There we go. That's where it gets used. And don't tip over easily. So, why is that important? Well, if the center of mass of the object is up here, it's going to be easier to tip over than if the center of mass of the object is located, down at the bottom. An object will not tip over until its center of mass is above the tipping point. So if you, and anybody who plays sports knows, if you don't want to get pushed over by the guy who's running at you, you're supposed to lower your center of gravity to make you harder to tip over. That's what we're talking about. So gravity is acting on the whole object, but for the purpose of calculating how an object behaves, we act as though the gravity is acting on the center of mass. That's why there's a difference in the word, but don't confuse them. We just say that gravity acts at the center of mass. That's a complicated phrase, so people just say center of gravity instead. All right, so just don't be confused by that. Now, the truth is, center of mass is a weighted average. That's all it is. Mathematically, it's a weighted average. But technically, the center of mass is a location. So when you're asked to calculate the center of mass, you're calculating a place, a location. There are two ways to calculate center of mass. Neither one of them any fun. And I want to be as understanding as possible that you may not understand the second way of doing it. And so I'll have plenty of time, because they've only asked for a student to calculate the center of mass using the second way once in the last 30 years. So I'm not too concerned. If it shows up. You've lost the roulette wheel, spin, but that means everybody in the country also won't know how to do it. Very few times does it ever come up. But the first way I'm going to show you comes up all the time. All right, so we're going to talk about the first way, which is pretty simple. It's a summation. So in a center of mass, let's assume for the time being we have three objects. We have a plank, and we have two boxes. Okay? Each object has a center of mass at its own center. We'd like to find the center of mass of the three object system. Okay? Now, the process we're about to learn is called the point mass calculation. It's how to calculate the center of mass if you can treat your objects like point masses. Does everybody understand what I'm saying? If you can break your objects up into point masses, then you can use the point mass calculation. Now, how do you know when you can do this? You can do this any time unless they tell you not to. Meaning, they don't have to say anything. If they say you have a box, a person, and a car, you can assume you can use the point mass calculation. The only time you would not be able to is if they say something like, you have an object of uniform density, and here is its shape. Then it's going to be something else. But they'll tell you when you have to use the other way to do it. Almost every other way, it's like this. Now, the way to do it is super, super simple. Let's, you guys like numbers better than not having numbers. So let's say that this box is 5 kilograms. Let's say this box is 5 kilograms. Let's say the plank is 10 kilograms. And let's say the plank is 10 meters long. And this is half a meter. And this, need one more distance, so I'm trying to draw it in here. This is 7 meters. Okay? We want to calculate the center of mass of the system. I'll remind you, the center of mass is a place. It's a location. So you should start a problem by saying, is your problem 1, 2, or 3D? Can you treat it like a one-dimensional problem? Do you have to treat it like a two-dimensional problem? Or can you treat it like a three-dimensional problem? Notice, I purposely didn't give you any height information. That's me sending you a signal that it is a one-dimensional problem. But first, just ask yourself, is it a one-dimensional problem, two-dimensional problem, or three-dimensional problem? 2. Identify a reference position. You need a reference place. They're saying to find the center of mass, which is a location. So where is 0? Sometimes they'll give it to you, sometimes they won't. I gave it to you, right? I made it pretty clear. I made all of my values measured from here. That made this 0. They won't always do that. You will have to choose a place sometimes that you're going to call the reference. Where is 0? Okay? But I want to impress this upon you. Center of mass is a location, which means it's a vector. So things on the right side of 0 are positive, and things on the left side of 0 are negative. Wherever your 0 is, you treat it like a number line, with positive values on one side and negative values on the other. Okay, I'm going to emphasize that again. The center of mass is a location. It is a vector. The next part is the calculation. It's the equation, and it's on your equation sheet. Since this is one-dimensional, I'm going to use x as my variable for the center of mass, and I will put x center of mass. I know that's all the way at the bottom of the board, so we'll get our little picture out of the way, and I'll do it right here. But that's going to equal, it's a sum. Sum of each mass and where it's located. You multiply it together. This is how you do a weighted average. And then we divide by the sum of all the mass. So again, the top is the weighted portion. We are weighting each mass by where it's located. And the bottom is us dividing out by the total mass of the system. So this is the total mass of the system. So, our question sits right here. Put the picture on the bottom, and we'll just do it. It's not hard. X, center of mass. I'm going to have a top and a bottom. Let's look at the bottom first. The bottom is easy, right? 5 plus 5 plus 10. The top, mass number 1, 5. Distance from the reference, 0.5. It gets very little weight because it's very close to the reference level. Mass number 2, 5. Distance from the reference level, 7. Mass number 3, 10. Distance from the reference level, where? I said it, but I hid it. I hid the answer. It's not 10. It's 5. That's right. I said that the center of masses of each object is at their centers. The plank was 10 meters long, but its center of mass is at the middle. You follow me? I'm not trying to trick you, but I'm trying to make sure you understand that that's the kind of thing they'll do. Objects have extension, so they'll do this kind of stuff. But that's it. You can do this, right? Center of mass is really pretty straightforward once you get the idea of what you're having to do. Many people struggle with the idea that the center of mass isn't a mass, but it's a place. And once you understand that, it's really straightforward. I don't care about the numbers. You guys understand the number part is the least interesting part here. But center of mass problems are going to be dynamic. They're going to have situations in which these objects are moving, and our job is to figure out how that affects the system. Obviously, this would have a shifting center of mass because the individual pieces are moving. So what we have to do in the next 2 days, because it won't take long, is we have to talk about the difference between the location of the center of mass and the velocity of the center of mass. It's not hard. I want you to understand something, that if you take all the x's and divide by time, they all become velocities. So it's not hard. All right.